Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. Deep within the constellation Scorpius, approximately 6,000 light-years from Earth, lies one of the most spectacular stellar nurseries in our galaxy, the Butterfly Cluster, officially designated Messier 6. This open star cluster, spanning roughly 12 light-years across, contains over 80 hot young stars that illuminate the surrounding cosmic dust with their brilliant blue-white radiance. The cluster earned its poetic name from the distinctive butterfly-like pattern formed by its brightest members, a celestial arrangement that has captivated astronomers for centuries. The butterfly cluster represents far more than a beautiful cosmic spectacle. It serves as a natural laboratory for understanding stellar birth, offering scientists a window into the fundamental processes that govern how stars form from the primordial material scattered throughout space. These stellar nurseries, technically known as star-forming regions, are where gravity orchestrates the transformation of cold, dark molecular clouds into the luminous beacons that light up our universe. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. To comprehend the significance of regions like the Butterfly Cluster, we must first understand the cosmic recycling process that makes stellar birth possible. Throughout the galaxy, vast clouds of hydrogen and helium, remnants from the Big Bang, drift through space alongside heavier elements forged in the nuclear furnaces of previous stellar generations. These molecular clouds, often called stellar nurseries, can stretch for hundreds of light-years and contain enough material to birth thousands of stars. The transformation from cloud to cluster begins when external forces disturb the delicate equilibrium within these cosmic cocoons. Shock waves from nearby supernovae explosions, gravitational interactions with passing stars, or collisions between molecular clouds can trigger the collapse of dense regions within the larger structure. As gravity takes hold, these collapsing pockets of gas and dust begin to heat up, eventually reaching temperatures and pressures sufficient to ignite nuclear fusion, the moment a star is truly born. The Butterfly Cluster showcases this process beautifully, containing stars at various stages of their early evolution. The cluster's massive blue giants, burning through their nuclear fuel at prodigious rates, represent stellar youth in its most energetic form. These heavyweight stars, some containing 20 times the mass of our Sun, shine with the brilliance of tens of thousands of solar luminosities, but will exhaust their fuel reserves in mere millions of years, a cosmic blink of an eye. Surrounding these stellar giants are numerous smaller, cooler stars that will burn steadily for billions of years, along with brown dwarfs, failed stars that never quite achieved the conditions necessary for sustained nuclear fusion. This diverse stellar population provides astronomers with a comprehensive snapshot of the star formation process, revealing how stellar mass, composition, and environment influence a star's ultimate fate. Modern astronomical instruments have revolutionized our ability to study stellar nurseries like the Butterfly Cluster. The Hubble Space Telescope has captured exquisite images, revealing the intricate structures within star-forming regions, while infrared observatories like the Spitzer Space Telescope and the recently launched James Webb Space Telescope can peer through the dust that often obscures these cosmic birthplaces in visible light. The study of stellar nurseries extends far beyond academic curiosity. Understanding how stars form helps us comprehend the chemical evolution of galaxies, the distribution of heavy elements necessary for planet formation, and ultimately the conditions that make life possible. The Butterfly Cluster and similar regions serve as time machines, allowing us to witness the processes that shaped our own solar system over 4.5 billion years ago. The birth of a star represents one of nature's most dramatic transformations, converting diffuse interstellar material into a concentrated nuclear furnace through the inexorable pull of gravity. Within stellar nurseries like the Butterfly Cluster, this process unfolds according to well-established physical principles that govern the behavior of matter under extreme conditions. The journey begins within giant molecular clouds, where temperatures hover around -260 degrees Celsius, just 10 degrees above absolute zero. These frigid environments contain primarily hydrogen molecules, with trace amounts of heavier elements and dust grains that serve as catalysts for chemical reactions. The density within these clouds averages only a few hundred particles per cubic centimeter, making them far more tenuous than the best laboratory vacuums on Earth. For star formation to commence, certain regions within these molecular clouds must achieve a critical density threshold known as the Jeans instability limit. This occurs when the gravitational attraction between gas particles overcomes the outward pressure created by their thermal motion. Once this threshold is exceeded, runaway gravitational collapse begins, with the affected region contracting under its own weight. As the collapsing gas cloud shrinks, conservation of angular momentum causes it to spin faster, while gravitational potential energy converts to heat, raising the temperature of the contracting material. This process creates a flattened, rotating disk of material with a dense central condensation, the birth of a protostar. The surrounding disk, known as a protoplanetary disk, often contains the raw materials from which planetary systems will eventually form. The protostellar phase represents a critical transition period lasting approximately 100,000 to 1 million years, depending on the final stellar mass. During this time, the central object continues to accrete material from the surrounding disk, growing in mass and temperature. Powerful jets of material, accelerated by magnetic fields, often emerge from the protostar's poles, clearing away nearby gas and dust while announcing the presence of the forming star to the wider cosmos. Nuclear fusion ignition marks the official transition from protostar to main sequence star. This occurs when core temperatures reach approximately 10 million degrees Celsius, enabling hydrogen nuclei to overcome their mutual electrical repulsion and fuse into helium. The energy released by this process creates an outward pressure that balances the inward pull of gravity, establishing the hydrostatic equilibrium that will sustain the star throughout its main sequence lifetime. The mass of a forming star determines virtually every aspect of its subsequent evolution. Low-mass stars, containing less than half the mass of our Sun, will burn hydrogen slowly and steadily for tens of billions of years. Solar mass stars like our Sun maintain stable nuclear burning for approximately 10 billion years. However, the massive blue giants found in the butterfly cluster, containing 10 to 20 times the Sun's mass, consume their nuclear fuel at such prodigious rates that they exhaust their hydrogen reserves in mere millions of years. The butterfly cluster's stellar population reveals the complex interplay between mass, temperature, and luminosity that governs stellar evolution. The cluster's most massive members shine with surface temperatures exceeding 30,000 degrees Celsius, appearing blue-white to our eyes due to their peak emission in the ultraviolet spectrum. These stellar giants produce intense stellar winds, streams of charged particles flowing outward at speeds exceeding 1,000 kilometers per second, that sculpt the surrounding interstellar medium and influence the formation of subsequent stellar generations. Intermediate mass stars within the cluster display yellow and orange hues, indicating cooler surface temperatures around 5,000 to 6,000 degrees Celsius. These stars represent a middle ground between the rapid evolution of massive stars and the leisurely pace of low-mass objects, typically spending several billion years on the main sequence before evolving into red giant stars. The cluster also contains numerous red dwarf stars, the most common type of star in our galaxy. These diminutive objects, often containing less than half the Sun's mass, burn their nuclear fuel so efficiently that they can maintain stable hydrogen fusion for trillions of years, far longer than the current age of the universe. Their longevity makes them prime candidates for hosting potentially habitable exoplanets, as any life that develops around these stars would have vast amounts of time to evolve and flourish. Understanding the stellar formation process within regions, like the butterfly cluster, provides crucial insights into the broader cosmic evolution of galaxies and the chemical enrichment of the universe through successive generations of star formation and stellar death. Modern astronomy has transformed our understanding of stellar nurseries, like the butterfly cluster, through sophisticated observational techniques that capture light across the entire electromagnetic spectrum. Each wavelength of light reveals different aspects of these cosmic birthplaces, creating a comprehensive picture that would be impossible to achieve through visible light observations alone. Optical astronomy, utilizing wavelengths detectable by human eyes, provides the foundation for our appreciation of stellar clusters. The butterfly cluster's distinctive pattern emerges beautifully in visible light, where the hot blue giants shine with peak intensity. Ground-based telescopes equipped with charge-coupled device cameras can resolve individual stars within the cluster, measuring their brightness, color, and position with remarkable precision. These observations allow astronomers to construct color magnitude diagrams, powerful tools that reveal stellar ages, masses, and evolutionary states by plotting each star's brightness against its color. However, visible light represents only a small fraction of the electromagnetic spectrum, and many of the most interesting phenomena in stellar nurseries occur at wavelengths invisible to our eyes. Infrared astronomy, which detects heat radiation, proves particularly valuable for studying star formation because it can penetrate the dust clouds that often obscure newborn stars in visible light. The Spitzer Space Telescope and the James Webb Space Telescope have revolutionized infrared observations, revealing the warm glow of circumstellar disks and the heat signatures of deeply embedded protostars. Infrared observations of the butterfly cluster region reveal a complex network of warm dust lanes and heated gas clouds that remain invisible to optical telescopes. These thermal emissions, typically occurring at wavelengths between 3 and 100 micrometers, trace the locations where stellar winds and radiation from young stars interact with surrounding material. The JWST, with its unprecedented infrared sensitivity and resolution, can detect individual protostars still in the process of formation, providing snapshots of stellar birth that were previously impossible to obtain. Radio astronomy opens yet another window into stellar nurseries, detecting emissions from neutral hydrogen atoms, molecular species, and synchrotron radiation from high-energy particles. The 21-centimeter hydrogen line, produced when hydrogen atoms undergo a specific quantum transition, allows astronomers to map the distribution and motion of gas throughout star-forming regions. Radio interferometers, such as the Atacama Large Millimeter Array, achieve remarkable spatial resolution by combining signals from multiple antennas, revealing the detailed structure of molecular clouds and the dynamics of gas flows around forming stars. Within the butterfly cluster region, radio observations detect emissions from various molecular species, including carbon monoxide, water vapor, and methanol. These molecules serve as traces of different physical conditions within the stellar nursery, with their emission patterns revealing temperature, density, and chemical composition variations throughout the region. The Doppler shifts in these molecular lines also provide crucial information about gas motions, allowing astronomers to map the three-dimensional structure and dynamics of the star-forming environment. X-ray astronomy reveals the most energetic processes occurring within stellar clusters. Young stars often exhibit powerful magnetic activity that generates X-ray emissions through several mechanisms, including magnetic reconnection events, coronal heating, and accretion shock heating in close binary systems. The Chandra X-ray Observatory and the XMM Newton satellite have detected numerous X-ray sources within the butterfly cluster, revealing stellar activity levels that far exceed those of mature stars like our Sun. The high-energy emissions detected by X-ray telescopes also trace the remnants of stellar evolution within and around the cluster. Shock waves from ancient supernova explosions, which may have triggered the initial star formation in the region, continue to heat the surrounding interstellar medium to millions of degrees, creating diffuse X-ray emission that illuminates the cluster's cosmic environment. Ultraviolet astronomy provides crucial insights into the hottest stellar atmospheres and the ionized gas surrounding massive stars. The Hubble Space Telescope's ultraviolet capabilities reveal the intense radiation fields produced by the cluster's most massive members, which ionize surrounding hydrogen and create the characteristic emission nebulae often associated with star-forming regions. The combination of observations across multiple wavelengths creates a comprehensive picture of stellar nurseries that reveals the complex interplay between stellar formation, evolution, and environmental effects. This multi-wavelength approach has become the standard methodology for modern astronomical research, enabling scientists to understand cosmic phenomena with unprecedented detail and accuracy. Advanced data processing techniques, including machine learning algorithms and computational modeling, help astronomers extract maximum information from these multi-wavelength observations, identifying subtle patterns and correlations that might otherwise remain hidden in the vast datasets produced by modern telescopes. The butterfly cluster represents far more than an isolated stellar population. It serves as a crucial component in the vast machinery of galactic evolution that has shaped the Milky Way over billions of years. Understanding the cluster's role in this cosmic process requires examining how stellar birth, evolution, and death contribute to the chemical enrichment of our galaxy and influence the formation of subsequent stellar generations. When the universe emerged from the Big Bang, approximately 13.8 billion years ago, only the lightest elements, hydrogen, helium, and trace amounts of lithium, existed in significant quantities. The heavier elements essential for planet formation and life, including carbon, oxygen, nitrogen, and iron, simply did not exist. These elements, which astronomers collectively term metals, could only be created through nuclear fusion processes occurring within stellar cores and during the explosive deaths of massive stars. The butterfly cluster's massive blue giants play a pivotal role in this cosmic alchemy. Within their cores, temperatures exceed 100 million degrees Celsius, enabling the fusion of progressively heavier elements through a sequence of nuclear burning stages. Initially, hydrogen fuses into helium during the main sequence phase. As the star evolves, helium burning produces carbon and oxygen, while subsequent burning stages create neon, magnesium, silicon, and eventually iron peak elements. When these massive stars reach the end of their brief but brilliant lives, they explode as supernovae, releasing the newly synthesized elements into the surrounding interstellar medium. A single supernova can eject several solar masses of enriched material at velocities exceeding 10,000 kilometers per second, creating expanding shock waves that sweep up and heat the surrounding gas. These supernova remnants can influence regions spanning hundreds of light years, distributing heavy elements throughout vast volumes of space. The chemical enrichment process creates a feedback loop that profoundly influences subsequent star formation. The heavy elements ejected by dying stars provide the raw materials for dust grain formation, which enhances cooling efficiency within molecular clouds and facilitates the gravitational collapse necessary for new star formation. Additionally, the shock waves from supernova explosions can trigger star formation by compressing nearby molecular clouds, potentially explaining the clustered nature of stellar birth throughout the galaxy. The butterfly cluster's age, estimated at approximately 100 million years, places it in a critical phase of this evolutionary cycle. The cluster's most massive stars are approaching the end of their main sequence lifetimes and will soon begin contributing their processed material to the galactic chemical inventory. Some may have already evolved beyond the main sequence, though their current evolutionary states require detailed spectroscopic analysis to determine precisely. The spatial distribution of elements throughout the Milky Way reveals the cumulative effects of billions of years of stellar evolution and chemical enrichment. Astronomers observe a clear metallicity gradient, with the galactic center containing significantly higher concentrations of heavy elements than the outer regions. This pattern reflects the galaxy's inside-out formation history, where star formation began in the dense central regions and gradually spread outward over cosmic time. Open clusters like the butterfly cluster serve as archaeological records of this chemical evolution process. By measuring the elemental abundances in cluster stars, astronomers can determine the metallicity of the interstellar medium at the time and location of the cluster's formation. Comparing clusters of different ages and galactic positions reveals how the galaxy's chemical composition has evolved over time and varies with location. The cluster's eventual dispersal will distribute its stars throughout the galactic disk, carrying with them the chemical signatures of their birth environment. Stellar dynamics and gravitational interactions gradually break apart open clusters over timescales of several 100 million years, releasing their member stars into the general galactic population. This process ensures that the chemical enrichment produced by each stellar generation becomes well mixed throughout the galaxy over cosmic time. Modern galactic chemical evolution models incorporate detailed stellar evolution calculations, supernova nucleosynthesis yields, and gas dynamics to predict how galaxies like the Milky Way acquire their observed chemical properties. These models must account for the complex interplay between star formation, stellar feedback, gas infall, and galactic outflows that regulate the chemical evolution process. The butterfly cluster and similar stellar nurseries also contribute to the galaxy's energy budget through their collective stellar winds and eventual supernova explosions. This mechanical feedback can drive galactic outflows that remove gas from the galaxy, temporarily suppressing star formation and redistributing heavy elements into the intergalactic medium. The balance between gas infall, star formation, and outflows determines the galaxy's overall evolution trajectory and its ability to continue forming stars over cosmic time. Understanding these processes provides crucial insights into the conditions that make galaxies like our own capable of forming the complex chemistry necessary for life. The study of stellar nurseries like the butterfly cluster stands at the threshold of a revolutionary era in astronomy, with next-generation telescopes and space missions poised to unveil unprecedented details about star formation and its connection to the emergence of life in the universe. These future discoveries will fundamentally transform our understanding of how cosmic processes create the conditions necessary for biological evolution. The James Webb Space Telescope, fully operational since 2022, has already begun, revolutionizing our view of stellar formation with its unprecedented infrared capabilities. Its observations of the butterfly cluster region reveal previously hidden protostars embedded within dense dust cocoons, providing real-time glimpses of stellar birth that were impossible to obtain with earlier instruments. The telescope's spectroscopic capabilities allow astronomers to measure the chemical composition of circumstellar disks, the birthplaces of planetary systems, with extraordinary precision. Future space missions will extend these capabilities even further. The European Space Agency's PLATO mission, scheduled for launch in 2026, will monitor over 1 million stars simultaneously, searching for the tiny brightness variations that indicate planetary transits. This mission will provide statistical insights into planetary system architecture around stars of different ages and masses, revealing how stellar properties influence planetary formation and evolution. The connection between stellar nurseries and planetary habitability extends far beyond simple planet detection. The radiation environment around young stars profoundly influences the retention of planetary atmospheres and the chemical evolution of potentially habitable worlds. The intense ultraviolet radiation and stellar winds from massive stars in clusters like the butterfly cluster can strip away the atmospheres of nearby planets, while also driving complex photochemical processes that may produce prebiotic molecules, essential for life's emergence. Ground-based telescopes are also undergoing dramatic improvements. The extremely large telescope, currently under construction in Chile, will possess a primary mirror 39 meters in diameter, nearly 4 times larger than any existing optical telescope. This instrument will directly image exoplanets around nearby stars and analyze their atmospheric compositions through spectroscopy, potentially detecting biosignatures such as oxygen, water vapor, and methane in the atmospheres of Earth-sized worlds. The study of stellar clusters provides crucial calibration for these exoplanet detection efforts. By understanding how stars of different masses and ages behave, astronomers can better interpret the signals from planetary systems and distinguish between geological and biological processes in exoplanet atmospheres. The well-characterized stellar populations in clusters like the butterfly cluster serve as natural laboratories for testing our understanding of stellar physics and planetary system evolution. Recent advances in computational modeling allow astronomers to simulate the formation and evolution of entire stellar clusters, including the complex gravitational interactions that shape planetary system architectures over time. These simulations reveal how close encounters between stars in dense cluster environments can disrupt planetary orbits, potentially ejecting planets into interstellar space or altering their habitability prospects through dramatic orbital changes. The chemical evolution traced by stellar clusters also provides essential context for understanding the prerequisites for life. The abundance of heavy elements in the primordial disk from which a planetary system forms determines the composition and size of rocky planets, the availability of water and organic compounds, and the potential for atmospheric retention. Stars that formed from metal-poor gas clouds billions of years ago may be less likely to host Earth-like worlds than younger stars born from chemically enriched material. Astrobiologists increasingly recognize that the search for life must consider the broader galactic context in which stellar and planetary systems evolve. The galactic habitable zone concept suggests that regions of the galaxy with moderate metallicity and low supernova rates may be most conducive to the long-term survival of complex life. The butterfly cluster's location within the galactic disk places it in a region where these conditions are favorable, making it a prime target for future habitability studies. The development of interstellar precursor missions, such as the proposed Breakthrough Starshot project, aims to send tiny spacecraft to nearby star systems within decades rather than millennia. While these missions remain technologically challenging, they represent the first concrete steps toward direct exploration of exoplanetary systems and the potential discovery of life beyond Earth. The study of stellar nurseries like the butterfly cluster ultimately connects us to our cosmic origins and our place in the universal story of matter, energy, and information. Every atom in our bodies, except for hydrogen, was forged in the nuclear furnaces of ancient stars and dispersed through supernova explosions that enriched the interstellar medium from which our solar system eventually formed. Understanding these processes provides profound insights into the conditions that made our existence possible and guides our search for life throughout the cosmos. As we continue to unravel the mysteries of stellar birth and evolution, we simultaneously explore the fundamental question of whether life represents a common outcome of cosmic evolution or a rare and precious accident in the vast expanse of space and time.